Okay, welcome back. So we're going to continue the proof of the general pinching theorem. So we are aiming to prove that we call our main assumption had been that the trace-free part of the Ricci tensor plus the Weil tensor are small compared to the scalar curvature in regions where the scalar curvature is big. This was our pinching assumption, and we had already shown, and then this assumption was made for all Pt in Mn across the time interval of existence, and then we had already shown that then there is a gradient estimate for the scalar curvature. We had shown that for any eta bigger than 0, there exists some c eta less than infinity, depending on the initial data and of course on this pinching condition constants, such that the gradient of the scalar curvature squared is less than eta times r cubed plus c eta. And this breaks the scaling invariance in the sense that this eta can be made arbitrarily small, whereas c eta is of lower order. And we had then proof using this gradient estimate that as t approaches t max, we must have that the minimum of the scalar curvature at time t divided by the maximum of the scalar curvature at t approaches 1. And this had been shown with the help of Miles' theorem. Now we want to show that as t approaches t max, that we can rescale the solution in such a way that after the rescaling, the solution converges to a metric which is smooth and has v and w identically 0, so it's a constant curvature metric. And we are in the positive setting here, of course. So it's a constant positive curvature metric, a spherical space form. Now, the key point is to do the rescaling. Now, there is different ways you can rescale Ricci flow. So we need to do a rescaling. And for this rescaling, there are different possibilities. So there's 3 different possibilities how you can do possibilities. The first possibility, and that's the one that Hamilton did in his original paper, and that we're going to use in a moment, is that you rescale in order to keep the volume constant. So rescale at each time the metric by a fixed factor. So you set g tilde of t is some psi of t times g of t, such that the volume of the rescaled metric is constant. U tilde volume of G tilde of T is identically equal to 1. Just fix the volume. Then, once you fix the volume, you have to, of course, prove that this achieves what you want. You have to show that then this new metric has bounded curvature, bounded above and from below, and then that this new metric converges to something smooth. The other way would be to, instead of prescribing such a volume condition, you could say, well, I'm expecting that the thing is going to converge to a sphere, and I know what the shrinking behavior of the sphere is. Just recall that on Einstein metrics, you get that the metric at time t is just the initial metric times 1 minus sigma times t, and the sigma is equal to, turns out to be equal to 2 over n times this constant scalar curvature. R0 is a scalar curvature of the initial metric. So this shrinks to length 0 at time t max is equal to the inverse n over 2 R0, and this means g of t would be equal to, another way of writing this would be t max minus t divided by t max times g of 0. So the factor here would be just the remaining time rescaled such that at time 0 you get the old metric. So here you could just rescale from this, take the try and rescale by g tilde of t for a general metric now, just rescale by psi of t times g of t, where the psi of t is equal to the inverse of this. So just take t max divided by t max minus t. So you would take this rescaling factor in order taking the lead from the spherical case. Then, of course, with this rescaling factor, you would have to also prove that the curvature then remains bounded and that the volume remains bounded, would not stay constant, but it hopefully would stay bounded, and prove that you get convergence in that sense. Now, this, of course, makes the assumption that you know this is the right blow-up rate. Now, turns out, in many situations, this is not the right blow-up rate. There are other singularities. And then it would be useful to have a further method of rescaling Ricci flow. In fact, it would be useful to have a rescaling of Ricci flow which takes you back again into Ricci flow. This is something we do later in the course, but it's worthwhile to mention this other method of rescaling here already, rescaling Ricci flow to Ricci flow. And this could be done in such a way, for example, choose a sequence of times, theta I, tending towards the maximum time, and points pi in sine not points. Take these factors towards the maximum time and just rescale the metric with these factors. So you take G tilde upper I KL at time, let me just see how to do this, at a new time tau, where you take theta I multiplied with the metric, the old metric, at theta I to the minus 1 tau plus Ti. Yeah, let's call it Ti. Yeah, got it wrong. You take Ti to T max and choose the factors theta I in R plus. So you take factors to rescale. Typically, you would choose, e.g., theta I to be the maximum of the scalar curvature over the manifold at time Ti. So, and you expect this to infinity, so to go to infinity, so you rescale the metric with larger and larger factors, but you introduce a new time variable tau, and this new time variable tau would then live in a space such that this is on the out time interval, so you would have theta I to the minus 1 tau plus Ti to be in the old time interval. So this would be between T max and bigger than 0, which is of course equivalent to saying that the new time variable would be between, on the one hand, theta I times T max minus T, and on the other hand, it would be bigger than minus theta I to the minus theta I times Ti. And now, with this rescaling of both the metric and the time variable, you can compute that now this new metric with respect to the time variable, tau, you get d tau of G tilde I KL of tau. This would be the theta I times the time derivative of this one, but then you get, of course, the t with respect to tau of, right, you get the inner derivative, so you get ddt of G KL, and here's KL, at theta I to the minus 1 tau plus Ti times the inner derivative, and the inner derivative here is exactly the theta I to the minus 1. So this would cancel out, and you just end up with the evolution equation of the metric GKL at this time. But now remember that I said the scaling behavior of Ricci tensor KL is of degree 0, so this is just the same as minus 2 times the Ricci tensor of the GKL metric, and therefore you get back the evolution equation of Ricci flow. So you get for each I another solution of Ricci flow, which has just been dilated both in the space direction and in the time direction. Now, of course, then you have the task of proving that this procedure reaches a limit, and you have to prove a compactness theorem, which we will do much later. But you want to get a limit, a limiting Ricci flow, G tilde infinity, and this limiting flow would be a flow since theta I tends to infinity and Ti tends to T max, a finite number. This would tend to minus infinity, so you would get a flow up to some T tilde max, which may or may not be infinity, may be finite or infinite, but you get certainly a solution which exists on all negative times. And in our case, you would expect that you get a round metric shrinking to infinite time to length 0, starting from radius infinity. In our case, we would expect G tilde infinity of tau to be the metric on a round sphere shrinking from infinite radius at tau tending to minus infinity to radius 0 at T tilde max, which in that case would be fine. Okay? So that would be the picture in this rescaling of the whole flow in this parabolic setting. Now, this will be the method that is much more general and that we will use later on, but for the proof of the pinching theorem, we will now use the original rescaling that fixes the complete volume that was used by Richard Hamilton in his original paper. Okay, so now use the rescaling G tilde of t equals psi of t times G of t such that V tilde of t is the volume of G tilde of t is identical to 1. Now, what is the time derivative of the volume form, right? So d v tilde is the square root of the determinant of g tilde times dx in local coordinates, and this is, of course, psi to the n over 2 times square root of determinant of g times dx. So this is psi over n over 2 times d mu. And so in particular we get that v tilde of t is equal to psi to the n over 2 times v of t. And therefore we get that 0 is equal to the derivative of v tilde of t. So we get that this is n over 2 times psi to the n minus 1 over n over 2 minus 1 and times psi dash of t times phi times v. And on the other hand, we get from the derivative of the volume, we get that plus psi to the n over 2 of t multiplied with the time derivative of the volume. And we have already seen that the time derivative of the volume is minus the scalar curvature times d mu. So this being equal to 0, we see that we can solve this and we get that ddt of log psi, psi dash over psi, the psi times n over 2 cancels, must be equal to 2 over n times the integral of the scalar curvature divided by the volume, which is 2 over n times the average of the scalar curvature. So R of t is the integral over the volume, is the average the scalar curvature. So we get this evolution equation for psi, and if we then introduce a new time variable, tau of t is just the integral from 0 to t of psi of SDS, then we compute that with this, since then d tau dt is just psi, and so we compute that dd tau of g tilde of tau, this is psi dash, so this is ddt of psi of t times t with respect to d tau times g plus psi times the derivative of g again by the t d tau, which gives us a psi to the minus 1 here, so we get ddt of log tau of log psi from here times g, and we get from here minus the dt, this just cancels, so we get plus ddt of g. So we get from here a minus, from ddt g, we get minus 2 times the Ricci curvature of g from this term here, and from here we get plus what I had computed here, 2n over r, 2 over n r times g. But now, again, using the scaling of these terms, which is invariant under psi, so this is nothing else but minus 2 times Ricci tilde of g tilde plus 2n over r tilde times g tilde. And this is now the new evolution equation. d tau of g tilde satisfies this evolution equation. So here you see the different nature of the rescaling that we have here. We get a slightly different evolution equation. We have not rescaled in such a way that we get exactly Ricci flow back again. We have rescaled in such a way that the new evolution equation has an extra term, and of course, since r tilde is a constant, the fixed points of this equation are exactly the Einstein matrix. So this equation is just, the solution is just completely fixed, doesn't change on any Einstein metric, in particular on the matrix of constant curvature that we are interested in. This metric just doesn't move. So the hope is now that we can prove that for our initial data, the solution of g tilde will smoothly converge to the limit that we want. Now, the task now is to prove that the curvature is so controlled and that the metric actually does this convergence. Now, what did we prove already? Now, since we are at each time rescaling the metric by a fixed factor, anything that we have already proved that is scaling invariant will survive to the new metric. So, I have already shown the following. Well, that's by our assumption, we have that the rescaled trace-free Ricci tensor and the trace-free remaining part, the wild tensor, divided by this. This is scaling invariant. So this is the same as v squared plus w squared on r squared, because the quotient is scaling invariant, and by assumption, this was less than r to the minus delta. And we already know that r tends to infinity and the minimum tends to infinity as well. So this thing here converges to 0 as t tends to T max. Right, so this we immediately know that this quotient will tend to 0 on the rescaled matrix G tilde. Also, we know that the quotient between R min and R max, this is of course scaling invariant, and we know that this converges to 1. Okay. So this is the things that we already know. Now the next step is to show that we can get an upper bound on the curvature. So here's the lemma. There exists a constant C1 less than infinity such that the maximum of the scalar curvature after rescaling is less than this constant. Proof. Well, since property 1 here from 1, we know that the trace-free part of the Ricci tensor tends to 0 compared to the scalar curvature. Therefore, it follows the trace-free part is very small. So the trace-free part, what was that? That was that was this tensor. This is the trace-free part. So this tensor can be made as small as we want compared to R times Gij. For T tending to T max, sufficiently close to T max. So in particular, we must have that R tilde Ij is bigger than, say, 1 over 2n times R tilde times Gij for R tilde for T close enough to T max. Okay. But then we have by Meyer's theorem that the diameter of the metric G tilde cannot be too large. It must be less than some constant depending on n times R, the minimum, right? So this is bigger than the minimum to the minus 1/2. But this must mean that the tilde. But this must mean that the volume, right, and this is of course, say, less than 2c times n times R tilde max to the minus 1/2, because R min and R max are approaching each other. So I have this comparison, but this must mean that the volume of this metric, G tilde, is less than a constant depending on n times R max to the minus n over 2. Right, if you have upper bound on the diameter, you must have a corresponding upper bound on the volume. And this, on the other hand, immediately gives us the upper bound on R max. So the volume, which is equal to 1, right? We have rescaled things such that the volume is equal to 1. So the lower bound on the volume gives us a upper bound on the scalar curvature. Now, what we can also prove is a blow-up rate for the scalar curvature. This is still a theorem on the original Ricci flow, which we then translate to the scaled one. So the next lemma says that the exists a constant C2 less than infinity, no, bigger than 0, such that the maximum of the scalar curvature at time t without the tilde, before the rescaling, blows up at least with the rate 1 over T max minus T. Remember, this is the blow-up rate that we expect from the sphere. So it's just saying it's behaving like it should. And the proof just looks at the evolution equation for the scalar curvature. So we have ddt of the scalar curvature for the original flow was Laplace r plus 2 times the Ricci square. Now, in view of our pinching condition, this is less than Laplace r plus 2 times r max squared. Or maybe, yeah. Yeah, it should, at least for late times, because the trace-free part is small compared to the scalar curvature part. Maybe I should write 4 times. 4 t. Yeah, let's just write constant here. Just be careful. Constant, depending on our pinching condition. For all t. Okay. And now, because at the maximum point this is less or equal to 0, this of course means that we have an ODE for the maximum. So we get ddt of R max less than constant times R max squared. Which means that if I take ddt of the inverse, then this is equal to minus R max to the minus 2, of course, all in the sense of difference quotients, times a constant times R max squared, and here I get the lower bound. And this now tells me, and this is just minus this constant. So now this tells me that R max inverse at T max minus R max inverse at some time t earlier, that this must be greater than minus this constant times T max minus T. But on the other hand, I know that R max goes to infinity, so this term here is 0, and I conclude that indeed, putting this on the other side and taking the inverse, I get that R max at T must be greater than 1 over C times T max minus T as required. So in other words, the upper bound on the evolution equation gives me a lower bound on the blow-up rate of the scalar curvature. So I have a definite bound on the scalar curvature, which now, of course, because the R min is comparable to R max, I must get that the R min T is blowing up by essentially the same thing, maybe factor 2. Okay, so I have a minimum rate of blow. Now, very similarly, I can use now the evolution equation for R in the other direction. So this is the first part. Now I can use exactly the lower bound to get that R min is R min of T is less than a constant over T max minus T. And the proof goes similarly. You do ddt of R. Now, instead of estimating from above, you do ddt of R is bigger than the Laplacian of R plus 2 Ricci squared. And Ricci squared is bigger than 2 on n times the scalar curvature squared. So you get that ddt of R min of T is bigger than 2 over n of R min squared. Actually, we did this already in the first lecture. Now, using the same trick of converting this to an evolution equation for the inverse of R min, we come to this conclusion as before. So now we have and then of course the maximum is also bounded by this. So we get, as a conclusion, everything together, we get that the scalar curvature everywhere must be both bounded from above by T max minus T, because the maximum of the scalar curvature is compared to the minimum, so it satisfies this upper bound. And on the other hand, from what we just proved here, it's also bounded from below by T max minus T. Okay, so we have now shown already that the scalar curvature has exactly the blow-up behavior that we expect. Now, what we are missing so far, however, is a definite lower bound on the scalar curvature. We have an upper bound on the scalar curvature, but no, not a lower bound on the scalar curvature. And you might expect that since we fixed the volume, that you could also get now a lower bound of the scalar curvature easily, just like we got an upper bound on the scalar curvature out of Meyer's theorem, because we got an upper bound on the diameter, and then we now also get a lower bound on the curvature, because we have a bound on the volume. So you need a lower bound on the scalar curvature. But this is not so easy. It cannot be too simple. Consequence of the fact that the volume tilde of G tilde is equal to 1. Notice the two following behaviors, so examples. We could have the first example is just the cylinder S1 cross some other manifold n minus 1, and take here the this radius to be the radius r. Then you notice that in this case you have a metric. So, for example, if this here is a torus, let's take S1 cross S1 T3, and suppose this radius is very small. So, suppose the metric here that we have is something like ds1 squared tensor ds2 squared, so the usual length on S1, but then take r squared times ds3 squared. In other words, make this factor very small. Then the curvature is completely zero. The Riemann tensor is identically zero, but the volume of T3, depending on this parameter r, tends to zero as r tends to zero. So we have complete control on the curvature, but we have no control on the volume whatsoever. This is often called collapsing phenomenon. So we cannot expect in general to be a very strong relation between volume and curvature. So just fixing the volume to 1, we cannot expect to get from that knowledge about the curvature. Now you might say, okay, maybe it has something to do, this is zero curvature, maybe what about other positive curvature? Here's examples. Take S3. Take this to be S3 divided by the group of isometries that come from R4, where you have on R4 the circle symmetries on one factor R2 and the circle symmetries, the discrete circle symmetries on the other factor, and you look at these discrete groups of isometries on the one circle with P and the other one of order Q, and then these are compact manifolds of constant curvature, quotients of the standard S3, but as the order of P and Q gets larger and larger, the volume goes to 0. The volume of these manifolds tends to 0 as PQ get larger and larger. So here you have the same constant curvature, but somehow the volume depends heavily on the group that you divide by. In other words, on how large the fundamental group is. Again, the volume might go to 0, although you have complete control over the curvature of the manifold. What is wrong in both of these examples, so this is example 2, yes, in both of these examples, what is wrong is the fact that the injectivity radius of the manifold tends to 0. Here the injectivity radius is some of order little r, and here the injectivity radius gets smaller and smaller as the distance between the points on the circle that make up the isometry in R2 and in the other factor R2 in R4 gets closer and closer. So the problem is the injectivity radius in both cases. Okay? So this is now really one of the fundamental issues in Ricci flow, one of the fundamental difficulties, how to control the injectivity radius, because you need a control on the injectivity radius before you can take any rescaling limits. So in the next lecture we do a short discussion of injectivity radius and how we can use our particular situation, the positive curvature and the pinching, to control the injectivity radius and get around this problem.